Next, we are going to study how we are going to we have studied about smart objects, sensors, actuators, wireless sensor networks, and MEMS, that is a microelectrical mechanical devices, right? Now we have to study how we are going to connect these smart objects together. How it is possible to these devices we want to connect it into the connected into in the IoT devices and sensors must be connected. So in what way, in which way we are going to connect it to the network for that there the data to be utilized. In addition to the wide range of sensors, actuators and smart objects that make up IoT, there are also a number of different protocols used to connect them. Okay, and in this topic, that is connecting the smart objects, right? So we are going to look at the characteristics and communication criteria that are important for technologies that smart objects employ for their connectivity, along with a deeper dive into some of the major technologies being deployed today. Communication criteria we are going to study to access the IoT technologies. The two main sections, the one is a communication criteria, okay. The another one is the communication criteria which describes the characteristics and attributes you should consider when selecting and dealing with the connecting smart objects. The various technologies used for connecting sensors can differ greatly depending on the criteria used to analyze them. Okay. And the other one is the access technologies, which are the access technologies we use for this. First, we'll take the communication criteria, right? So these communication criteria we are going to study range, signal preparation, propagation and distance, frequency bands, licensed and unlicensed spectrum, power consumption, stable power source or battery powered, topology, various layouts that may be supported for connecting multiple smart objects, constrained devices, limitations of certain smart objects from a connectivity perspective, constrained node networks, challenges that are often encountered with the networks connecting smart objects. So now if you take a range, constrained node networks, so constrained devices, limitations of certain smart objects from a connectivity perspective, and constrained node networks, this is going to highlight the challenges that are often encountered with a network connecting smart objects. The second main section of this topic is the communication criteria, IoT access technologies. They provide an in-depth look at some of the technologies that are being considered when connecting the smart objects. Currently, number of technologies connecting smart objects is quite extensive, but you should expect consolidation with certain protocols eventually winning out over others in the various IoT market segments. This intentionally limits the technologies for connecting the sensors to ones that seems to be most promising and going forward in the IoT marketplace. Other technologies are mentioned in context when it is applicable. Okay. So we'll take the communication criteria, that is access technologies. If you take, we have IEEE standard protocols, that is 802.15.4 and 8.2, 1.5, 0.4G, 4E, 2A, 1901.2A, 802.111AH, right? Low wireless area networks, NB, IOT, and other LTE variations. Okay, so let me take communication criteria. First one, in the world of connecting things, right? A large number of wired wireless access technologies are available or under development. Before reviewing some of these access technologies, it is important to talk about the criteria to use in evaluating them for various use cases and system solutions. Wireless communication is prevalent in the world of smart object connectivity. It mainly because it is the easy in the deployment and allows the smart objects to be mobile, changing the location without losing connectivity. So if you are going to take some examples which you are going to discuss in addition to the wireless connectivity, wired connectivity consideration also mentioned when it is applicable in the. So when you take a range, so see, you can see here the wireless access landscape, there is a short range, medium range and long range. So far does the signal need to be propagated. So what will be the area for the selected wireless technology? Should indoor versus outdoor deployment be differentiated? Very often, these are the first questions which we are going to discuss when we are going to take a wired and wireless access technologies. The simplest approach to answering this type of questions is to categorize the technologies in the down ranges, that is a long range, short range and the medium range. Okay. So in the above figure, you can see there, short range you have Bluetooth devices, medium range you have 802 Zigbee, and long range you can see the Wi-Fi, that is a 2G, 3G, 4G and the 5G. Okay, it mainly focuses on the IoT technologies to avoid the adding too much confusion by talking about all the multitude of IoT technologies in the market today. Okay, only one that appears to have strongest foothold. If you take a short range, the classical wired example is a serial cable. Wireless short-range technologies are often discussed as an alternative to serial cable, supporting tens of meters of maximum distance between the two devices. Examples of short-range wireless technologies are IEEE 802.15.1, Bluetooth and IEEE 802.15.7 visible light communication VLC. These short-range communication methods are found in only a minority of IoT installations. In some cases, they are not mature enough for production deployment. For more information on these IEEE examples, we can Google it on the Google it in the Google, right? So when you go for a medium range, so medium range you can see 802.15.4 GE Zigbee devices, Wi-Fi.h, Wi-Fi.ac, Wi-Fi.b, G and N. This range is main category of IoT access technologies in the range of tens to hundred of meters. Many specifications and implementations are available. The maximum distance is generally less than 1 mile between the two devices, although the RF technologies do not have a real maximum distance defined as long as a radio signal is transmitted and received in the scope of the applicable specifications. If you take a medium range wireless technologies, which they include these 802 series, and wired technologies such as IEEE 802.3, Ethernet, IEEE 1901.2, narrowband powerline communication, PLC may also classified comes under the medium range depending on their physical media. The characteristics, all the media range protocol just mentioned are covered in the long range devices. If you take the 2G, 3G and the 4th and 5th G distances, it is measured in the distances when greater than 1 mile between the two devices require long range technologies. Wireless examples are cellular technologies 2G, 3G, 4G and 5G, and some applications of outdoor IEEE 802.11 Wi-Fi and low power wide area technologies. These low power wide area technology communication have the ability to communicate over a large area without consuming much power. These technologies are therefore ideal for battery powered IoT sensors. And the other example mentioned found mainly in industrial networks, IEEE 802.3 over optical fiber and IEEE 1901 broadband power line communication are classified as long range but are not really considered as IOC access technologies. Okay. For wireless deployments, the maximum coverage expressed a specification product description is often derived from optimal estimated condition. In the real world, you should perform proper radio planning using the appropriate tools followed by a field radio survey or better understand the actual conditions over a given area. You also need to consider the environment factors such as the interference and noise and specific product characteristics such as antenna design and transmit power. Finally, you should be aware of potential landscape and topology ranges in the field such as the new buildings that may interfere with the signal transmission. Okay, so that is about the long range. When you take a frequency bands, that is a different ranges, right? Radio spectrum is regulated by countries under organizations such as International Telecommunication Union ITU and the Federal Communication Commission FCC. These two groups define the regulations and transmission requirements for various frequency bands. For example, if you take a portion of spectrum are allocated to types of telecommunications such as radio, television and military and so on. Around the world, the spectrum for various communication is used often viewed as a critical source. For example, if you can see the value of these frequency by examining the cost and mobile operators pay for license in the cellular spectrum. When you are going to focus on Internet of Things access technologies, the frequency bands leverages by wireless communications are split into licensed and unlicensed bands. Licensed spectrum is generally applicable to IoT long-range access technologies and allocated to communication infrastructure deployed by service providers, public services, for example, first responders, military, broadcasters, and utilities. An important consideration for IoT access infrastructure that wish to utilize licensed spectrum is that users must subscribe to services when connecting their IoT devices. This adds more complexity to deployment involving large number of sensors and other IoT devices. But in exchange for the subscriptions fee, the network operator can guarantee the exclusivity of the frequency usage over the target area and can therefore sell a better guarantee to the better services. So we can see that improvements have been made in handling the complexity that are inherent large number of devices in the licensed spectrum, thanks to the development platforms such as the Cisco Japper Control Center, automating the provisioning the deployment, used for IoT accelerometer, WiMAX, narrowband, NB, IoT technologies. So exceptions exist in license spectrum. For example, the digital enhanced cordless telecommunication wireless technology operates in the license bands centered in 1.9 gigahertz, but no royalty fees apply. Therefore, ultra low energy is defined as an IoT wireless communication standard in license spectrum, but what happens is it does not require a service provider. The ITU has also defined an unlicensed spectrum for industrial, scientific and medical portion of the radio bands. These frequencies are used in many communications technologies for short-range devices. Unlicensed means that no guarantees or protections are offered in the industrial, scientific and medical um, portions, bands for device communication. Even for IoT access, these are the most well-known ISM bands. That is a 2.4 gigahertz band used by the IEEE 802.1. Then IEEE 802.15.1 Bluetooth, IEEE 802.15.4 WPN. The low range of IEEE Bluetooth limits usefulness in most of the IoT deployments. An unlicensed balance, that is a band such as those in ISM range frequencies, is not unregulated. National and regional regulations exist for each of the allocated frequency bands, much as with a license band. These regulations mandate device compliance on the parameters such as transmit power duty, cycle and dwell time, channel bandwidth and channel hopping. Unlicensed Unlicensed spectrum is usually simpler to deploy than licensed because it does not require the service provider. However, it can suffer from more interference because other devices may be competing for the same frequency in a specific area. This becomes an element in decisions for IoT deployment. Should an IoT infrastructure utilize unlicensed spectrum available for private networks, or we can use the licensed frequencies that are dependent on the service provider? Various low power wide area technologies are taking on the greater importance when it comes to answering this question. So in addition to meeting low power requirements, so low power wide area communications are able to cover long distances that are fast required the licensed bands offered by service providers for the cellular devices. Some communications within the ISM bands operate in the sub-gigahertz range. That sub-gigahertz bands are used by protocols such as IEEE 802.15.4 and G and AH, and low power wide area technologies like LoRa and SignFox. All these technologies play a very important role in the IoT networks. The frequency of these transmissions directly impacts how a signal is going to propagate and its practical maximum range and its importance to IoT access or further indoor and outdoor deployments. The sub-gigahertz frequency bands allow greater distances between the devices. These bands have better ability than 2.4 gigahertz ISM band to penetrate building infrastructure or go around obstacles while keeping transmit power within the regulations. The disadvantages of this sub-gigahertz frequency, however, is the lower rate of data delivery compared to higher frequencies. However, So, however, most of the uh, uh, IoT sensors do not need to send data at high rates. Therefore, the lower transmission speeds of sub-gigahertz technologies are usually not a concern for IoT sensors deployments. If you take example, in most European countries, 169 megahertz band is often considered the best suited for wireless water and gas metering applications. This is due to its good building basement signal penetration. In addition, the low data rate, this frequency matches low volume. Okay, so this is all about the the access technologies. So you should take into account the frequencies and corresponding regulation of country when implementing or deploying IoT smart objects. Smart objects running over unlicensed bands can be easily optimized in terms of hardware supporting. The two main worldwide sub-gigahertz frequencies are 868 MHz and 915 MHz. However, parameters such as transmit power antenna and EIRP must be properly designed to follow the setting required by each country's regulations, whether it is in India or Europe, whatever it may be. We must be very specific when we are going to deploy these kind of things. So when you take a power consumption in the IoT devices, okay, so definition of IoT device is very broad. There is a clear delineation between the powered nodes and battery powered nodes. That is a inbuilt power and the external source of power. So in a powered band node has a direct connection to a power source. The communications are usually not limited by power consumption criteria. However, it is very easy to deploy a powered node is limited by availability of the power source, which makes mobility more complex. Battery powered nodes bring much more flexibility to IoT devices. These nodes are often classified by the required lifetimes of their batteries. Okay. Does a node need 10 to 15 years of battery life, such as water or a gas meter, or as 5 or 7 battery life sufficient for devices such as smart parking sensors? Their batteries can be changed or the devices replaced by the street gets resurfaced. For devices under regular maintenance, the battery life will be around 2 to 3 years is an option. IoT wireless access technologies must address the needs of the low power consumption and connectivity with the battery powered nodes. This has led to the evolution of new wireless environment known as low power wide area LP. That is a LPWA. It is possible to run just about any wireless technology on a batteries. However, in reality, no operational deployment will exhibit acceptable if hundreds of batteries must be changed every month. Wired IoT access technology consisting of powered nodes are not exempted from the power optimization. In case of deployment of smart meters over a PLC, the radio interface meters can consume 5 to 10 watts of power. On this will add up to 20 millimeter deployment, which is going to consume around 100 to 200 megawatts of energy for communications. Okay, that is all about the next we'll go for the communication criteria where we can perform the with the topologies also. So if you take some of the topologies, right? So you have studied the computer networks, that is a different topologies which are going to make the communication of each node. So different topologies are available.